Potential and activation energy. As you can see, these reactants over here, they need to hit a certain threshold up here. Okay, in the white, it's going to be more difficult than it would be to hit the green segmented peaks, right? So the green segmented peaks here, if there's 3 of them, that means that there's going to be 3 steps in the reaction mechanism. Therefore, the activation energy is going to be much lower. How is this possible? It means that a catalyst like an enzyme was involved to decrease the amount of activation energy needed for a successful collision. Why is this important? Well, it ensures that there's no uncontrolled release of energies. For example, a spark, it's uncontrolled, it's too much too fast, okay? We want to control. Well, where can we see this happen? We can see this happen when the electrons are carried in the ETC via the NADH and FADH2. See my 20-minute video where I explain this diagram in detail. Next, we have here in this graph on the very left, okay, we're going to label the terms appropriately. So our X and our Z here is going to be our reactant and product. How about our Y? Our Y is that threshold that we're trying to achieve. So this will be our activated complex. Okay, whenever we reference the activated complex with a substance in question, whether that's reactant or product, let's first deal with our product here. Okay, so as you can see here, for Z, that is our product. So the difference between the activated complex and that one is going to be our activation energy, and it's going to be in the reverse direction. Why reverse? Because our reaction always proceeds towards the right. We're dealing with the product here, so it would be the reverse direction. The activation energy here would be for number 3 in the forward direction, because we're dealing with activated complex and the reactant in this case. All right, for our PE, because technically this here is our PE chart, if we start at 0 and then we go up to our Z, that means that is our PE metric. Okay, that's going to be the PE for Z. You can do the same thing for X and Y for number 5 and 6. Okay, number 4 is our catalyst, like we said at the very beginning up here. It makes it easier for the collisions to occur and that the reaction can proceed. Number 7 here would be our delta H, the energy release, as determined here, enthalpy. We can determine the activation energy by observing the reaction rate at various temperatures. What does this mean? So let's look at B. It says reactions with high EA are generally slow at room temperature. Why? Let's have a look up here. Okay, if it's higher up, that means that there are less reactant particles able to hit that, so lower probability. That means that there's going to be less of them coming into product over here. That means there's going to be less electrons or less energy that is going to be released in that process. It's going to be slower. Okay, it's going to be a slower rate, so therefore it's going to be a slower rate of reaction. For A, what is the meaning of the term EA? It's the minimum threshold to be obtained to allow a reaction to proceed. Okay. Next here we have 10 to the 28 collisions. Okay. How come they don't react and complete instantaneously or spontaneously very easily? Well, even though there's many collisions, number 1, maybe there's not enough energy to overcome that EA activation barrier threshold, or there's an insufficient amount of geometry orientation so that they align really well with one another, the particles between them. Okay, both of these here need to be met in order for an actual reaction to occur.